Hello, this is video P, and it's still about functions, except all I want to talk about on this one is reference parameters. And I'm sorry in advance, just as you got into a comfort zone with functions from the last video, video O, and you got parameters all figured out. I don't know how that works. Those are blanks that have to be filled in. You would be right, except there are some limitations of the way that was done, and this is to try to overcome some of that. How was that for a teaser? I put my notes down somewhere. I've been having technical difficulties. I'm sure you can tell. This is the second chance to try to get this video. I almost had it all the way through and then it quit. Wah. Again. Okay. Here's another function. Let's write a function. This is nothing new right here, though. This is another function. I'm dropping down on the board, so I've got room to put a sketch of the main program up there. I learned my lesson from last time. Void, I'm going to call this swap ints. Guess what this is going to do? Hey, you're right. It's going to try to swap the value to integer variables. Try to. Why not just do it? It is going to swap the values of int A and int B. Short variable names so I can spell them. They were longer in the crashed version of this video. But anyway, open curly bracket. Like so. And what could be simpler? A equals B. B equals A. Done and done. It swapped them, and that's why that's a void function. There's no reason to send anything back. And let's do a pretend trace of this pretend function. Let's say, I don't know, maybe the main program in the first position of the actual parameter list passed in a 10, and for B it passed in a 27. I just made those up. There's no significance to the numbers whatsoever. And let's trace it and make sure it works the way it's supposed to. Takes the value of B and makes that the new value of A. Then it takes the value of A and makes that the new value of B. Whoops. You knew better than that. Yeah, your eyes have been rolling. You lean back and nod knowingly. I know what's going on. Yeah, that's not going to work. So let's fix it. We need a temporary variable. We need a holding place so that we don't trash the old value of the original variable. You know, it's easier just to write it. Int temp. Think fast. What is temp? You're right. It's a local variable. It's not going to exist until we get to this function. We don't need it until we get to this function. We need a temporary holding place to be able to swap these two. Now we can say temp equals A equals B, and B equals temp. Still no return value. Now, strangely, I could put return, semicolon, without anything following it, and it would go back. But you know what? When it hits the closing curly bracket, it's going to go back anyway. So I don't have to have a return statement in a void function at all. When it uses up all the statements, then it goes back. So we're not sending anything back. Let's do my pretend. And of course, I don't remember what I used for A and B. Something in 27, I think. But I'm tired of those. -3 and 100. And away we go. So those are values that would have been hypothetically passed in from the main program. So first, so good. Then, poof, as if by magic, temp appears over here. Initially garbage, indicated by a question mark. And then we get an assignment statement. Take the value of A, make that the new value of temp, -3. Done. Take the value of B, make that the value of A. 100 becomes the new value of A. Done. We're almost there. I think, yeah, one more. B equals the value of temp. B equals temp, -3. And voila, as if by magic. Now A is 100 and B is -3. Okay. Seems to work okay. Now, I think I did the main program in purple last time, so I'm going to do the main program in purple this time. Here we are in main, and I'll just make up a couple of integer variables. Int x short variable names in this one. I'm tired of writing long ones and messing up my hand trying to erase them. X equals 75, comma, y equals 4. And let's call our brand new function swap_ins. Now, we don't say x equals swap_ins or y equals swap_ins or anything. That would actually be a compiler error because we will have to have a prototype for swap_ins up above the main. I'm just assuming that we absorbed all of that from video O. You got to remember all that function stuff and then roll this in. But it's going to check and make sure that I send in two things, but I don't try to save a return value anywhere because there ain't no return value. Swap_ins. Shut up and write. Okay. Swap_ins and I pass in x and y. And when I get back, I'll print them out. Cout, less than, double quote, x equals, and close double quote, less than, x. Takes a long time to write these, doesn't it? Less than, double quote, space, y equals, close double quote, less than, y. And I won't even bother with an inline. Probably should. But double quote, and moving on. Here's a trace. And I'm doing the traces in hot pink for whatever reason, or more likely for no reason. But here is x, and here is y. X is 75, y is 4. Now, the very next line calls our function. It's not the right-hand side of an assignment statement. This is just going to do whatever this function does, and then pick up where it left off when the function's done. So here we go. Here we go, traveling down to our function, our little mini program down here. It's got local variable, not local variable, excuse me. Formal parameter A, that looks like a 9, but it's an A. Formal parameter B. And local variable temp, initially garbage. And, well, whoops, I got ahead of the game. A and B, those receive values from above. X is the first thing, so X is value 75 is going to land in A. There we go. And B. B gets whatever is sent in the second position in parentheses, and that's Y. The value Y is 4. So 4 goes into B. Now I'm caught up. Now a variable temp appears. And away we go. Temp equals A. The 75 goes right here. B. B is 4. 4 goes into A. And temp goes into B. Temp is 75. 75 goes into B. There we go. It swapped them. No return statement needed. No return value allowed. It's void function. So go back up and pick up where we left off in the main program. Here we are. We just got back from function swap_ins, and it hits the cout statement next, and our output is x equals, well, let's see, value of x is 75. Y equals, value of y is 4. Done and done. What could be simpler? Well, maybe nothing is simpler, but something would be more correct. Look at this. We started off with x equals 75, y equals 4. We called swap_ins. You had one job. And we got back, and they are not swapped. They're untouched. They're unchanged. This line is in the way. That output is depressing. It's kind of sad. How about a blue note? Here's a blue note. Separated from code above, separated from code below, in a whiteboard segment of its own. By default, pause and reflect on that for a second. Default means what happens automatically if you don't do something to change it. So by default, parameters, P-A-R-A-M-E-T-E-R-S, two functions, F-N apostrophe S, plural functions. Parameters to functions are passed by value. That's a two-word phrase that's used to describe it. In other words, when this function was called, uh, the system looked to see what the value of x was, and it was 75. And it threw the 75 down here to land in the first slot in parentheses. It looked at the value of y. The value of y is 4. Throw that 4 down there to land in the second parameter. And it did. We did get the 75 and the 4 down here. We got the values that were sent in by the main program. The problem is this. We did all this work and swapped the values that they sent us, but those values got swapped in our local formal parameters, things that only exist for the function. And when the function goes back, it takes all that work with it. It takes back the newly changed values of a and b when those variables disappeared. I've got a dash here, that's not a period. By default, parameters to functions are passed by value. The bottom line, the practical matter of that is, functions cannot, C-A-N-N-O-T, cannot change the values of any variables back in the caller. I don't have room for back, so I'm just going to say in the caller. And I'll read this back and see if I can explain it. Here's the situation we ran into with the pink mess down here and the pristine pinkness up here. By default, if we don't do something special, parameters to functions are passed by value. Functions cannot, double underline, cannot change the values of any of the variables back in the caller. This swap ints, since it only got values, copies of the values of those variables back in main, it did not have the power to change the value of x or to change the value of y. It's quite sad. What are we going to do? Well, that is a limitation of only being passed by value. You know what we're going to do? Pass by reference. Get rid of this blue sad note. I'm going to try to leave this code on here. I might regret that. But, you know, the way things have gone today, I'm probably going to have to redo this video anyway. So maybe I won't leave all that code on the board in the next iteration of this video. I feel like I'm talking to myself at this point. It's been such a horrible mess of a day that way. I can't do that. Bye, main. I'll put you back when I need you. This is an aside. Tell you a little story. Aside. I'll even put it in a square bracket like that because it's not really with the flow of discussion of parameters and functions and all stuff. There are two values associated, ASSOCIATED, with each variable in memory. Colon. Number one is, or I'll just use dash, its value. Well, we're overloading that word, aren't we? Two values associated with it. One of the two values is its value. The other one is its address, ADDRESS. And that is what it sounds like. That's where it lives in memory, in computer memory. Every variable has a unique address represented in zeros and ones, represented in shorthand and hexadecimal. So here's a fig to go with that. Let's say I've got a variable called total. Why not say that? And let's say total is currently 120. Well, there's something invisible here that we, up to this point, have never written along with the variable or its value or anything. This lives in a very specific location that no other variable lives in. I'm going to make it up. I'm going to say it lives at hexadecimal F3B0. F3B0, where did I come up with that? I just made it up. Just like I made up the 120 as the pretend value. Since addresses in memory are always represented in hexadecimal, shorthand for binary, because that's what it really is. It's a binary number. You're going to see weird addresses that look like that, except they've got a lot more hex digits in them. And if you need to look up hexadecimal to understand how I can get away with writing something like that as a number, then you might want to pause the video and look up hexadecimal in Wikipedia or something. But that is a legitimate number. It's just homemade. Now, I've talked way too much about that, and I'm sorry. What did I just do? What's that figure for? Well, 120 is the value. That's the value of variable total. This is the address. And I could fill up the whole whiteboard with all the different characteristics of those numbers. Here's the salient here, the important part. That value can change, otherwise that's not really a variable. It can change. I can say total equals 0 and start all over again. I can say total equals 75, whatever. It's a variable. The address, however, is not only unique to this variable total, but it's unchangeable as long as the program is running. When your program is loaded into memory by the loader, there is an address associated with variable total, and that's where that variable will live throughout the entire lifespan of your program. So once the main program gets loaded into memory, total, in my pretend example, went to, that's a small x there. It's kind of hard to tell. Looks like a Greek letter, doesn't it? It's a small x, F3B0. If that's where total got loaded in with your executable code, then that's where it will sit, as long as the program is running. And then when your program's done, it's all cleaned out of memory. You run it again, maybe total goes somewhere else in memory, but once it gets assigned a memory location, total owns that memory location. No other variable can go there. I'm making a big deal out of that, am I not? Well, you know what? I'm going to close off the aside. That was our little walk down hexadecimal land, the two values associated with variables. It's an important idea, but now it's taken up valuable real estate on the whiteboard that I'm going to have to reclaim. Sorry about that. So here we are again, back at Purple main program. I left a blank line up there on purpose. Main, and my integer variables, int L, capital L. I'm mixing it up. See what I'm doing? L is 304. And I made that up. Almost all these numbers that I'm making up, hexadecimal, decimal, whatever, those are arbitrary and pretend. LM equals 133. There. Excellent numbers that I chose for myself. This pink stuff, oh my goodness, that's been gone a long time. As soon as we got back from the function, all of that stuff had disappeared. Now, I'm going to change things up a little bit. Instead of, I'm actually going to leave all the green stuff on the board. I'm going to have to move back in to make some space. And move back this in to make some space. There. Now that's exactly the way it was before. Except I widen the space. Why would I do that? Because I'm going to do this. I am going to put an important and visible, as soon as I find a marker that can do it, ampersand, right after int. How important is that? That's so important. I'm even going to go to the blank line I left up there. Oh, I can't keep up with any of my markers. It's gone. Oh well. Up here, I'm going to put the prototype. It's got to be the same as the first line. Void, swap ints, parentheses, int, and I'm going to leave space because I'm going to make that pink again. Space, A, comma, int, big space again, B. Since it's a prototype, close parentheses and semicolon, Remember, all this is, that prototype has to be there, but that's a mental note to the compiler. But we're actually sending the compiler a different message this time than we would have if I left it like that. With this ampersand, what that's doing, let me annotate that. Tells compiler these are passed by reference. R-E-F-E-R-E-N-C-E. By reference. And I don't know why I left my purple code hanging like that. But I'm going to go ahead and call swap-ints. Swap-ints. Multitasking board. Pass in L, pass in M, and cross my fingers and hope I get better luck this time. When I get back, I'm going to do a cout, print out the value of L, colon, space, double quote, L, less than, double quote, space, M, colon, space, close double quote, less than, M, semicolon. That's the main program. This is still down here. This is my function down here. And let's see. Tells the compiler these are passed by reference. So the compiler knows what passing by reference is. We just don't yet. Let's see if we can catch up with the compiler. Here's my trace over here. L has initial value 304. I'm going to put L down here. No, I'll leave it up there. Sorry about that. I'm setting myself up for disaster. I can tell already. L has initial value 304. If you could read my mind, you'd know what I was talking about. M has initial value 133. Oh boy. Here we go. What else do we need to know about L and M to pass by reference? We got to know where they live. If we know where they live, we can go to their house and mess them up. If we've got a clone of them, if I got a clone of L, I might mess up the clone. It doesn't touch L at all. That's a problem we ran into with the original swap-ints. But if I know the address of L, I can go in there and mess with it. Hexadecimal 1280. There's a more normal looking number. Maybe M lives at hexadecimal 4B0E. Again, there's no significance to those. Those are hexadecimal because they represent addresses. The only significance is they have to be different from each other. L and M are different variables, so they can't live at the same location in memory. Every variable has its own unique memory address. And you're going to call me a liar in just a second, because here we go. Swap-ints LM. Now this, except for the variable names, this looks like just like the call to swap-ints we made earlier. And on behalf of the C++ syntax designers, I apologize for that. You can't look at the call and see that these are being passed by reference. The compiler looks at the prototype and the function itself and says these are not passed the old-fashioned way. These are not passed by value. These are passed by reference. What that means is it's not passing 304 and 133. It's passing the address of where those variables live. Let me say that again. When this function is called, L and M, it is not sending to the function 304 and 133. Because these are set up with the ampersand, the all-important ampersand, it's passing by reference, which means it passes in where those variables live in memory. So it's passing in hexadecimal 1280 and hexadecimal 4BOE. And here they are. They arrive down here at the function. Hexadecimal 1280 and hexadecimal 4BOE. Those addresses are associated with new names. A, B. It does not make brand new variables in memory for formal parameters A and B. It associates new names with old variables. That variable already exists. It's known as L back in the main program. The function, inside the function, it's known as A. It's like your mom calls you Billy and your dad calls you William. You're still the same person. We've got two different variable names for exactly the same memory location. I make this a ghostly or a dotted box because if I were to print out the value of A right now, I would indeed see 304 and it would look like Somebody passed me a 304, but they did not. They sent me a hexadecimal 1280, which happens to be the address of where that particular 304 lives in memory. B's got the same life story over here. They didn't pass in 133, even though it looks like it. They didn't pass in 133. They passed in the address of where that particular 133 lives in memory, back up in the main program. So we've got address 4BOE. We know where that variable in the main program lives, and we are going to call it by our own local variable named B. So if we were to print that out, we would certainly see the 133, but your eyes deceive you. You're seeing double. How much have you had to drink today? Those two 304s are actually one and the same. If I could fold the whiteboard so that that one laid on top of that one, those two are identically the same 304. They live in one and only place in memory. Same thing with 133. 133, again, your eyes deceive you. You're seeing double. Those two 133s are actually the same number located in that one unique memory location, 4BOE. All that complication. Now, to some degree, we revert to business as usual. Int temp. It looks simple now, doesn't it? Local variable. It does spring to life. It has its very own memory location, which, by the way, memories are laid out is usually real high. FF08. A very high hexadecimal number, but that's irrelevant. That's still a homemade number. It's just that it did not exist. It was not carved out of memory until just now. And that memory that it used to carve it out, when the function goes back, it's still going to throw that back and say, you know what, I'm not using FF08 anymore. We can use that somewhere else if you want CPU. Okay, so here's where we go. I don't know. I'm going to try this with purples. Temp equals A. I think I can do that with purple. A is 304. Well, it looks like 304 because A is a pseudonym for that 304 up there, so we're copying the one and only one 304 right here. Not much to that. A equals B. Here's where things get weird. B appears to have value 133. What this is actually telling the computer to do is copy that 133 into memory address, the memory address associated with variable A. A lives at 1280, so does L. So when we copy 133 to 304, I feel good, I feel strong, I think I can do this. Good word about this the whole video. 133. Well, that wasn't so bad. Yeah, okay. Why did I even try to do that? It's not that there were simultaneous changes. There was one and only one change. As soon as I copy 133 to address 1280, it's going to appear, if I turn around and do a cout, it's going to appear that A has value 133. When I get back, if I want to print out L, I have to clean that up. It's going to appear to be 133. See how this works? If you didn't, well, you get another shot. Look at this. We just did A equals B. B equals temp. Down here, this local point of view down here, that's just taking the 304 and putting it right there. What that's doing is copying the value of temp, which is 304, and putting it at the address where variable B lives. Variable B and variable M live in the same place, which is even kind of an erroneous way to say that. B and M are actually the same variable. There's one and only one memory location, 4BOE. So if I take temp 304 and put that in memory location 4BOE, let me see if I can do this more better. It does this. 3. This is looking good. O. Ah. I knew it. 4. There. I didn't want to do them in sequence because it made it look like, well, it did this and then it did that and all that. It all happened at one time. Those 304s, those are actually one and only one 304 that lives at address 4BOE. Now then, all of this stuff, all of this mess down here. We hit the end of the function, our name for that memory location disappears, our temp variable disappears, all this stuff disappears. And we're done. It goes back where it came from. And when we generate output up here, output L colon, and the value of L, 133. Space M colon, the value of M, 304. Look, started off with L equal to 304, M equal to 133. We called our new improved version of swap-ins that uses reference parameters to swap the two values. And yes, as if by magic, the two values are swapped. The bottom line is, we got over that blue note that I put sandwiched in the middle here. If this needs to make changes to the variables, the corresponding variables that are passed in from the main program, and we want those changes to stick. In other words, we want them to stay changed when we get back to the main program. It's got to be passed in by reference. You got to pass in with the ampersand. If you want this swap ins to be able to swap those two, exchange those two, and make it stick so they're still swapped when you get back to the main program. That's actually kind of a vulgar way to describe it. I mean, that is the effect of what happens rather than what really happens. What really happens was that messy picture I drew over there with the addresses and all that. And it is important to understand that because that's going to come back and bite us if we don't understand it later on in summer school. What else could I possibly say about reference parameters? Well, look at the example carefully, maybe even run it, maybe even modify it. And I don't know, you could experiment. You could make one of the parameters does the swap function reference and the other one value and see what that one does. Oh, there's all kinds of stuff you could do to mess it up. But I do want to carve out a space and put a parting note up here. Note, this is a purple note, not a blue note. We don't have time to get into this in depth, but you know what? We can extend our Zoom class meeting or Zoom office hours as much as we need to discuss this at great length. By default, well, you know what? I don't even say by default because I don't know of a way to change it. Arrays are passed to functions by reference automatically. And that's the corresponding phrase, by the way. By reference. Arrays are passed to functions by reference automatically. Which means if you decide you want to write a sorting algorithm, I don't know, bubble sort, you'll have to pass in an array. Otherwise, it's not going to have anything to sort. But you don't have to put any ampersands or anything. You only use the ampersands for individual variables to indicate to the compiler that you want to send the address down to the function, not just a clone copy of the value. That happens automatically with arrays. When you pass an array to a function, that function knows where the array lives, and if it starts juggling things around in there to sort or whatever, when you get back to the main program, the array that you sent in will also be all juggled around and sorted or whatever. Now, that bears additional discussion, I know, but please look at the deluge of example programs that you have for this video, the previous video, and the previous video to that. I would say go through those in detail beyond how they were described in the videos and write notes on them if you've got hard copies, or type up notes separately if you're just looking at the example programs in a window on the screen, because remember, those are an essential part of our text for this class. And I put those out there so that you have additional examples and what ifs and so forth to study, and then we can discuss those as much as we need to in the Zoom sessions. But in the interest of time, I've already taken up a lot of time. In the interest of time, I'm probably not going to go into great detail in those examples that are attached to the email in other videos. And I know I'm rambling. I'm tired. It's been a long day. And I'll see you online.